Recording.
Good day, everybody. Good morning, good afternoon, good evening. I can see from the chat that there's people joining us from many different places. So whatever time of day it is for you, you're welcome. Thank you for joining us today for this. I'm sure it's going to be a fascinating talk, how to image a black hole. And we're very excited about this particular talk. Well, we're excited about all our talks, but this one we are very excited. I'm sure that many of us will remember that iconic photo that literally hit the headlines worldwide in 2019 of the first image of a black hole. It really went across the board, so all different countries, all different types of news outlets. It really was amazing. And that image was created by something called the Event Horizon Telescope, which is not a single telescope, but a group of telescopes, an array of telescopes across the world, all working together. And we are very honored to have with us the co-founder of the Event Horizon Telescope, and that is Professor Heino Falke, who you can see in front of you there. Professor Falke has a very impressive resume. As I said, he co-founded the Event Horizon Telescope and was chairperson of its scientific council until 2019. He's since 2007, he's been a full professor of astroparticle physics and radio astronomy at now I'm going to try and say this correctly, Radboud University in the Netherlands. May not have
It's Radboud, but okay, it's close enough.
Thank you very much. Okay. Yeah, so he received his PhD from the University of Bonn and then did his postdoc at the University of Maryland and is also a visiting professor at the University of Arizona, as well as being a staff scientist at the Max Planck Institute for Radio Astronomy in Bonn. So we are really very excited and very honored to have Professor Falke with us today. And we are very much looking forward to hearing all about how we image a black hole. So, Professor, please, over to you.
Thank you. And I'm glad that I can do this here finally. We tried to schedule it a little bit and it works today. So I'm glad to see. And I've even seen some familiar names now in the Zoom. I'll share my screen and I hope that works. Oops, going back. And just to say that this, of course, work that's happening in a large collaboration with many people with the Event Horizon Telescope collaboration. And my own work has been funded a lot by the European Union via European Research Council's Synergy grants, in fact, 2 of them by now. And if you want to find more details about the story, then you can look at, if it's still available, in these books, which have appeared in multiple languages, actually. Now let's start from the beginning when we talk about black holes. And that was a major shift in our understanding of how space and time and gravity actually interact and how they belong together. Albert Einstein published his general theory of relativity, which changed our perspective of gravity. Gravity after Newton became a force. And after Einstein, it became a property of space and time, so to speak. What his model was, his picture was that matter would actually twist, change, bend space itself. And the only true constant is no longer absolute space and absolute time that we think are sort of as rigid, solid, unmovable things, like space is always there, time is always marching forward. No, the realization was the true constant of nature is light, or particularly the speed of light. Because with light, we actually measure space and we do measure time. And it turned out that wherever you are, in what system you are, the speed of light is always constant. And the speed of light is a ratio, of course, of a length divided by a time. Like if you have a car, it tells you it's going with a speed of whatever, 50, 100 kilometers an hour. In some countries, they still use miles. And so miles an hour. And so the ratio between length and time is sort of fixed, but length and time themselves can change. And then matter comes along, and matter has mass, and mass, according to Einstein, actually bends space-time. And so that's a picture we have. Sort of, we have a two-dimensional representation of space. You have a solid body with a lot of mass, and it will actually bend space-time. Now, three-dimensional space-time we cannot picture very well, so we make this two-dimensional representation. We pretend space is only two-dimensional, and then it's like, creating a little funnel by putting something into onto this space. If it's stretchable surface, so to speak, you put a stone on it, and then it will actually create this little funnel-like thing. Now, light will still follow the trajectories of space and time, the space-time, but it will be deflected. It can no longer go on a straight line. And in fact, as space is stretched, it has to take a longer route, so to speak. However, it still goes with the same speed. You should still measure the same speed as there, even though it goes a longer length. So if you want to preserve that constancy of length divided by time, also time needs to change. If you stretch space, time needs to stretch. At least that's what you measure. If you measure a stretched space, you measure a spread time. And you do this because time is also a clock. Light oscillates. Sorry, light is a clock. It oscillates. So it's like a pendulum of a clock swinging back and forth. And as you spread or stretch space, the pendulum, so to speak, has to make longer swings, or you have to make longer steps, so to speak. And so that's what you see here, that the dot's supposed to represent sort of the ticks of time. And as you bend space, also time seems to be stretched. And so this is how these two things are interlinked. I hear some noise, by the way, and someone may mute him or herself. Now comes the next trick. Schwarzschild, just a few months later, actually he was in the First World War, calculating how cannonballs would fly. He was at the actually Western Front near France in Germany. He was a Jewish scientist working in the German military, and who actually died soon after that engagement. He calculated, he was a brilliant mathematician and astronomer. He calculated how space would look like if you had a point mass. So all the mass of the sun, for example, condensed in a little tiny point. And then the equations of general relativity became actually weird, so to speak. Namely, light would actually stop. It would stop at this point where this matter would be. Light normally would flow through space and time forever, and we're not taking absorption or emission into account in this picture. It's just pure vacuum, more or less. But if there's a singularity, i.e. in space-time, that's created by matter condensed in a point, then light will actually stop at this location. And light would be infinitely spread and stretched, so to speak. And already, well before you hit the singularity, that's where the matter is point-like, and therefore also the curvature of space-time is infinite. before you reach that point, already you have a virtual membrane, so to speak, which we call the event horizon. And the event horizon has a dimension which is given by this formula 2gm over c squared, where m is the mass of the object, g is the gravitational constant, and c is the speed of light. These are the fundamental constants of the system. And once you've crossed that point or that surface, it's actually if you have a spherical body, it's actually a shell, a virtual shell around that singularity in the very center. Once you've crossed that, nothing, not even light, can come back. Because light, the speed of light, is the fastest velocity in the universe. It's a velocity of information. And so once light has entered that region, it cannot come back, cannot come out of this event horizon. I sometimes picture this like a waterfall. So if you have, a little river going into a waterfall, if you're a good swimmer, you can maybe swim against the current of that river. But once you've gone over the waterfall, there's no way you get back, and at the bottom of the waterfall, you hit the bottom, so to speak, and are crushed. And that's exactly what happens in a black hole. Space actually drags you down the waterfall at some point, and you'll be crushed in the singularity once you get in. So that's the basic picture we have of black holes. Now, Einstein didn't really believe these things would exist, let alone that you could see them. So how does a black hole look like? Could you actually see this? Well, that's how a black hole would look like. Well, actually black on a black background. Now there's this virtual surface, which I've drawn here as a gray ball. And the only way you could see a absorbing object on a dark background is by shining light at it. Let it be surrounded by light. And that's what we do here by trajectories of light. These are essentially laser rays to shoot at a black hole, just to illustrate the properties of light around a black hole. And what you see here is that light is bent. The closer you come with your laser beam to the black hole, the stronger it will be bent. And there is this one point where light will actually even go in a circle around a black hole. And there's also a interesting trajectory on the other side of that black hole, where actually light goes forward, then turns back, and then enters into the black hole. And what we see here is the consequence of the rotation of the black hole. The black hole rotates, and therefore it actually drags space with it. It's like a big eddy in the ocean or whatever. So if the water goes this way, then boats will be dragged with that eddy, and well, maybe if we actually sink. And that's exactly what's happening here. Space goes backward, and light turns around and then enters in the event horizon. But for our purposes, to understand what we're seeing, that region is important where actually light will go around in a circle even. And that's just one tiny little one ray that will actually go in the circle. We'll come back to that. Now, let's look at whether black holes exist in reality. I said that Einstein didn't really believe black holes would exist. Nature has proven him wrong in that aspect. What we see here is a Hubble Space Telescope image of a galaxy at about 2 billion light years away. Optical light, nothing spectacular. Well, any of these images are spectacular. But then if you add a radio image on top of it, you see a small jet shooting out of radio emitting material. And that structure actually extends about 1 million light years. And the energy in these plasma outflows, as we now know they are, the energy can be, the total energy of all the stars in our Milky Way, or even 10 or 100 times more than that. So it's just, energy of 100 to 1,000 billion stars, all generated in a region that has the size of the solar system. So how can you create such an enormous amount of energy? Well, the idea is that we have a black hole, which is surrounded by plasma or gas. That gas spirals around the black hole because of angular momentum conservation, but actually it loses some angular momentum, so stuff falls in because there's some magnetic friction involved. It heats up, and in fact, as it comes close to the black hole, it starts to rotate with almost the speed of light. That's because the escape speed is speed of light, the rotation speed is almost speed of light as well. And if two bodies hit each other with the speed of light or close to the speed of light, there's an enormous amount of energy involved. In fact, as you know, kinetic energy goes with the speed squared. And if you go to this almost speed of light, energies of even the tiniest bit of matter are just absolutely staggering and enormous. You can calculate how much energy this is. If you ask yourself how much energy per time could this process generate, it's about a few percent to 40%, typically you say 10% of the mass per time that's flowing in times c squared. And mc squared, looks familiar because that's the other famous formula of Albert Einstein, which is energy is mc squared. The energy is the matter times speed of light squared. So that's the maximum energy you can sort of have in matter. And so a significant fraction from all the energy that's sort of in matter can be created. If you calculate, I did this for the Netherlands, how much energy you need to generate all the power needed in the Netherlands, which has 16 million people, 18 now, I think, and for all forms of energy, transportation, heating, electricity, and so forth, then it would be enough to have 10 buckets of water and pour it into a black hole. And that water would actually heat up so much, get so much kinetic energy, that it would produce so much energy that for an entire year, you would have all the energy you would need. So this is how you can get the energy right. And again, the scale of this is small. Black holes are tiny, given by the Schwarzschild radius, and I'll show you in a moment how much that is. And so by this combination, with very efficient energy production and small scale, and strong gravitational attraction, people were always suspecting that black holes are the culprit for these powerful radio jets and some other phenomena like quasars and so forth. So that's this. But then let's look at the size scale. So we have on the bottom, we have the masses of black hole. On the left, you have on the y-axis, you have the sizes corresponding to these masses. And so if you have a neutron star, which is sort of the remnant of a exploding star, large star, then you can compress this star to something like a few tens of kilometers. That's the size of a city, essentially. If you have an even bigger star exploding and compressing its inner parts, you can have actually a black hole with a few solar mass, 3 to 5, up to 100 solar masses we've seen so far. And then you would have the size of an island or large island or something like Iceland on Earth. So these are cosmic objects with Earth-sized or geographic features. And then you go to supermassive black holes, which are in the centers of galaxies, probably, and there's still a big debate how these things actually come about. Potentially at the beginning of the universe, the inner parts of a galaxy collapsed. That's a more likely scenario these days, I gather. Then you can have actually a black hole the size of 1 million times that of the sun, like 1 million stars, essentially. And it would be somewhat larger than our sun. And then we have sort of monster black holes, which have 10 to the 10 solar masses, which would have the size of the solar system. So still small on cosmic scales, that would be large for human scales. And that's the interesting thing about black holes and neutron stars. They cover really all scales, from human cities to solar system size. And that corresponds to also timescales. Black holes, stellar mass black holes of milliseconds to second timescale. Supermassive black holes and galaxies like ours have minutes to hours timescales. And then supermassive ones, they vary on days to weeks. That could be that fast. And they all produce jets. And these jets actually have much longer timescales. For stellar mass black holes, they vary between minutes to years. Even longer timescales for supermassive black holes, days to millennia. And on these really, really large jets, you can have up to 100 million years that you see essentially covered in one jet, because these jets actually extend over a million light years, right? Because they have so much power. So this is an enormous range that you cover by studying black holes, from really tiny to really galactic huge. So then if you want to image a black hole, you want to have something that is large on the sky, okay? And that depends on the size of the black hole, i.e. its mass and its distance. And so if you have a stellar mass black hole in our Milky Way, then typically that would be at a few thousand light years or a kiloparsec away. That would be 0.1 nano arc seconds. I'll tell you, this is, for all practical purposes, unobservable for now. If you go to the Milky Way, however, which is the closest galaxy of ours, it's our own, we are sitting in the Milky Way. It is a standard spiral galaxy. So of all the standard spiral galaxies, this would be the closest to ours. It's at about roughly 8 kiloparsec distance, 27,000 light years. It has a few million solar mass black holes. We'll come to that. And then the size would be 20 micro arc seconds. The example I always give is that this would be sort of a little hole that you drill into a mustard seed at the distance at New York, as seen from probably Accra or from Europe. So it's essentially across the Atlantic. You see a little mustard seed and smaller than that. Now we'll see that actually is observable. And then there is another relation. It looks like that the more massive black holes fit in more massive galaxies. Again, there's someone making noises here. So the larger the bulge of a galaxy, the larger is the black hole. And where are the largest galaxies in the universe with the largest bulges? Well, these are in the centers of clusters. Sometimes you have galaxies, like 1,000 galaxies orbiting each other. And then some of them actually merge, and then they form a monster galaxy in the center of this cluster of galaxies. And it turns out the most massive or largest nearby cluster of galaxies is the Virgo cluster, and the central galaxy is the galaxy M87, the famous galaxy M87. And so it has a black hole of 6 billion times the mass of the sun. And that means that would be sort of the closest of the monster galaxies in our local universe. And if you calculate how big that one would be, it's about 16 microarc seconds. This would be the scale in Schwarzschild radii. We'll see in a moment that actually a black hole becomes bigger. So they have very similar scales on the sky, even though they are at very different distances and have very different sizes. And I'll like to give an example how this, why this is so, just to give you an intuitive feeling. This is the Cologne Cathedral, nearby where I live. It's a massive, fantastic, big cathedral. And here I'm holding, I don't know if you can see this, a little scale model of that cathedral, which is 1,500 times, or actually 2,000 times smaller than that cathedral. I think 1,500 times. And then actually I move 1,500 arm lengths across the river and hold it 1 arm length away in front of me. And then, perspective makes it appear as if the scale model and the real model have almost the same size. And that's exactly what's happening here. The little one, the scale model is, so to speak, is the tiny, in quotation marks, black hole in the center of the Milky Way. And the other one, the big cathedral in the background, which is further away, is the massive black hole in M87, which is 1,500 times bigger and 2,000 times further away. But, for some weird reason, the mass difference and the distance compensate almost exactly. And that's one of the many factors of luck we had in this project, where the universe just conspired to help us, see this object. Now, if you look at the radio image, or if you look at how M87 looks like, this is the galaxy here. You see the spiral galaxy. You see this little thing of light sticking out of there, which was discovered very early on, 100 years ago already. And you make a radio image. You see it also has these classical radio jets shooting out of the very center. And that radio plasma that shoots out of the center actually fills a huge bubble of gas, a few 100,000 light years around the entire galaxy. So that plasma is actually engulfing the entire galaxy. That's how much. And this is still one of the weaker radio galaxies we have, by the way. And then this is the radio image of the center of our Milky Way. And what you see here, this is actually, you see the plane of the Milky Way and a bright region in the very center. Some of these bubbles are actually exploding, like supernovae remnants of former exploding stars. The bright one and at the left is actually a star-forming region, and in the very center we have what's called the Sagittarius A complex. Sagittarius from the constellation of Sagittarius, A because it was the brightest radio source, therefore Sagittarius A. Turns out what we see there actually in the very center, the bubble is actually probably another supernova that exploded 40,000 years ago. In fact, I think 40,000 years ago, we all were running around in Africa, actually. And so had we had radio telescope then, we could have seen a beautiful radio supernova explode. So we were just a little bit late with our radio astronomy, unfortunately. It would have been a spectacular, view. Can you again mute yourself, please? Those people have joined. Thank you.
Hello, please. Sorry, just 1 minute. Hello, please. There's somebody called Suka Nasiru. Could you please mute yourself?
Otherwise, I'll do that myself.
Thank you.
Okay. Well, this is this Sagittarius A, and then we'll continue here. And then we see actually what's in that structure there. This is what's called the mini spiral. That's actually gas rotating around the black hole. And in the very center, you have a little tiny dot of radio emission. And that was, discovered in 1974 and was since then suspected to mark the central location of our black hole. So that's the radio picture. And we've been hunting these things actually for decades, essentially, trying to get closer and closer and getting higher and higher images. Now, what was very important in the center of our Milky Way was some other development. This is an optical picture of our Milky Way. If you are in the night sky, you see this beautiful band of lights in the night sky. You see essentially our own Milky Way edge on. That's because we're living in this disk of gas. 100 billions of stars are you actually seeing there? And the dark regions, the dark patches, are clouds of dust out of which stars form. Unfortunately, if you use an optical telescope and want to look to the center of the Milky Way, you have to look through all this dust, and that absorbs your light. You cannot see through it. But what you can do is switch to other telescopes, and that we'll do here in this animated zoom. We'll switch to near-infrared views, near-infrared light, which is longer wavelengths than red, essentially redder than red, so to speak. And then you can see actually the light of stars from the very center. And these are pictures taken here by the group in Garching, which shows essentially how stars over 16 years thereabout move and in fact rotate around the very center. And if you look at this one particular star, you see that it's almost on a perfect ellipse. An ellipse, you may remember, this is what the planets, the orbit of the planets around the sun. And that's exactly what these stars do. Like planets around the sun, they orbit around another point mass. In this case, we suspect it's the black hole. And from the speed, how fast they rotate, that's 8,000 kilometers per second if you go close to the turning point. So they go around with 8,000 kilometers per second. That means we need a lot of mass, a lot of gravity to keep you on an orbit. If you go around a curve with 8,000 kilometers per second, from that we can deduce a mass, and it's 4 million times the sun, the mass of the sun. And for that work, Reinhard Genzel and Andrea Ghez received the Nobel Prize a few years ago because they, very precisely measured the mass of that object. However, they were still factor 2,000 away from that black hole, right? It meant there was a very compact region, a lot of matter combined in a small place, that it wasn't telling us yet whether it's a black hole or not. And so we have to turn to other wavelengths. And that's what I did when I was young. I did my PhD on this particular object in the early 90s, and I was looking at the radio emission. So what you see here is a radio emission as a function of frequency. On the bottom line, you see a frequency, a picture frequency like the tones on the piano, right? So if the low pitch tones, the low frequencies on the left, and on the right side, you have the high pitch tones. So low frequencies on the left, high frequencies on the right. And this is, we're starting with gigahertz frequencies on the left, which is what your cell phones use, these kind of radio wavelengths. Microwaves is a few gigahertz. Then, if you go to 43 gigahertz, they're about, actually this radio frequency is typically used mainly for some communication devices on satellites. And then you go to above 100 gigahertz. These are actually wavelengths which are a millimeter or close to a millimeter or less. And these wavelengths or this radio emission or this emission is actually produced in these airport scanners that some of you might have seen. So that's the range of frequencies that we're looking at. And the y-axis, the vertical axis, gives you intensity, so how strong is the light. And the data points show you what's measured for the center of our Milky Way. You see radio emission, at your cell phone frequencies, and it gradually increases in intensity until it reaches these millimeter waves, and then actually cuts off. It stops. And so why is that, and what does it tell us? Well, the idea is that, if there's a black hole, matter will fall in. And actually, our black hole is, I called it in my PhD thesis, a black hole on a starvation diet. It doesn't eat too much. So it's only a little bit of matter that falls in. And therefore, the inflow is relatively, is not very dense, and it actually does not produce a lot of radiation, in fact. But it does produce these jets. And the property of these jets is they sort of shoot out from close to the black hole. They expand. The magnetic field will become less and less. And it turns out there's a characteristic frequency that, at each distance from the black hole, as you move away, the density will go down, the magnetic field will go down. Also, the characteristic frequency where the radio emission is produced will go down. So essentially, jets are like a rainbow, right? So red is on one side and blue is on the other side. And so if you want to see a certain part of the jet, of this outflow, then you have to pick the right color. And it turns out that sort of the highest colors in this model, the highest frequencies, the bluest color, so to speak, then translated to radio, happen exactly at a scale that is close to the black hole. At least that's what the model was telling us, or telling me at the time. So what I was seeing was, okay, if I look at sort of the red color, I'm far away from the black hole. I go to higher and higher frequencies, i.e. bluer and bluer color, so to speak. And then, I get to the small scale where I should reach the black hole. And then suddenly, there is no emission at higher frequency anymore. That was suggesting, okay, I get to the smallest scale. As I go to higher and higher frequencies, I get closer to the black hole, and then essentially disappears inside the black hole. Yeah, so that's the idea. So I would have to look at this region in this frequency regime if I want to see the black hole. I want to illuminate the black hole with light. And once more, we have someone in the line. Okay, so that's what we said. At these frequencies, we see this. I'll skip this part here. We calculated then how black holes would look like if you surround it by emission, and in fact turned out that this emission is, as we say, optically thin. Picture this like the flame of a candle, yeah, and so you actually can look through the flame of a fire, right? It's bright, but in principle you can look through it. And in the very center, there's this dark object, which is this black hole. And that black hole will be black and dark, and you would see this dark region. Now, okay, maybe I have to go back. After all, this additional effect, you're not only seeing the black object, you see the effect of it after essentially magnification. Because black holes bend light, they'll actually amplify or magnify themselves. And this actually, the mass for this was already calculated in 1916, believe it or not. So it was just, again, less than a year after relativity was created. And then this picture was made a few years later. But what you see is, again, light, if you look from the right, okay? And you look actually at a separation that actually usually would miss the black hole. But then actually it's bent towards the black hole, and it goes around in the circle, or in fact, it ends up in the black hole. So even if I look here, I will look into the black hole. And therefore, the black hole will appear larger than it actually is. And various effects, in fact, compensate so that whatever the black hole does, whether it rotates or not, whether you look from the bottom or from the side, whether the material around it rotates or not, it always gives you more or less this dark region, which we call the shadow of a black hole. Because you're not really seeing the black hole itself, you see the light that is missing. You cannot see a black hole. You can never see a black hole. You can only see its shadow, the missing light. And that's its telltale feature, the light that it absorbs. And so we predicted that, if you go to that frequency, if you look at the center of our Milky Way, based on our models, we should be seeing this shadow of a black hole. And it would be a very clear signature of black holes exist. Now, of course, the models have become much more complicated. Now, this is just to scare you, and don't even ask me to really understand all the details of this equation. But these are sort of the equations of relativistic magnetohydrodynamics, which means you follow the flow of matter in curved spacetimes. And so you have curved spacetime, and so you have tensors and metrics and so forth. But essentially, you have particle number conservation. So always you don't lose particles. You have momentum conservation. Momentum is conserved. You have energy is conserved, and the induction equation, which tells you how to deal with magnetic fields, and sort of an ideal situation where there is no currents produced, ideal conductor. And then you start with some initial conditions. You put some gas around the black hole. You have threaded with magnetic fields, and then you let it rotate because everything rotates at its local, as we call it, Keplerian speed, which means the inner parts rotate faster than the outer parts, because also their gravity is stronger. And after very short time, these magnetic fields are stretched and look like a bowl of spaghetti, more or less, right? So these are magnetic field lines. If you keep letting the simulation running, the magnetic fields are being wound up. And in fact, near the inner edge of this accretion flow, before it matter falls into the black hole, some parts of these magnetic fields are being shot out along the rotation axis. You saw the puffed up gas of disk. Now you can look at where is all the matter in this, and you can calculate how hot are electrons, which is a tricky question, by the way. And then you can calculate how would such a system look like. And I told you it's important to choose the right frequency. And so this here is a low frequency, and there you see the accretion flow, and you see the plasma jet shooting out. But now we go to gradually higher and higher frequencies. As we go to higher frequencies, suddenly the wheel sort of lifts, and you can start seeing the black hole. You see this ring. This is actually coming from where the light goes around and circles, and that's what you would expect. In fact, this is from a paper here, this image from 2016 with Monika Moszybrodzka, where we published a prediction for what we would expect to see in the case of the galaxy M87. This was a true prediction. In fact, all of these were true predictions because nobody had ever made images of how a black hole would look like under these circumstances. And again, that visible size would be 40 microarc seconds. That's because of this magnification effect. The shadow is larger than the black hole itself. Now, the question is, how can you see this mustard seed in New York from Europe or Africa? You need to build a telescope the size of the Earth at these wavelengths. The larger a telescope, the sharper it could be in principle, and the smaller the wavelengths, the sharper it will be, but the wavelength is fixed. So you have to build a telescope the size of the Earth. Which is unpleasant because most people will probably object if you cover the entire Earth with one giant radio telescope, and in fact would be a bit too expensive. But what we can do is we can build a virtual telescope, and that's the beauty of what we call interferometry, or in this case, very long baseline interferometry, because telescopes are separated by continent, really. And so now picture you have a radio telescope. What does it do? And you have a point source, like point source at a cosmic distance, and it will emit waves. And because they're so far away, when the wave arrives at Earth, this is almost a plane wave. It emits a wave coming in, which is always on the one side of the Earth, the same as on the other side of the Earth. Okay, that's what will hit the Earth. And then what a telescope does is very simple. It just reflects the light at the surface and makes sure that all the light bundles arrive at the focus at exactly the same time. That's the important thing. It needs to be so fine-tuned that the waves that come in on one side, they're oscillating on both sides, and then they're sort of propagating. And if they come to the surface, to the focus point, they are sort of have exactly the same length, or it took them the same time to arrive there. Okay, it's a bit complicated. So you have here, if you can look at my hands, I don't know, you have sort of one wave coming in on one side of the Earth, and here's the other coming in on the other. Then you want to make sure, and then you put them together exactly in phase, so that all the peaks and valleys are on top of each other. If one arrives a little later, shifted by wavelengths, then you have the peaks and the valleys lying on top of each other. And if you combine the two, they will actually destructively interfere. They will kill each other, right? So you have to make sure they arrive exactly what we say in phase on top of each other, and then they will constructively interfere and give a signal. So that's what a telescope does. But however, that combining of waves, you could do in the computer, okay? So rather than having the wave reflected here and being combined in the focus, you record it here, in fact, on hard drives with a proper timestamp, and you get a digital copy of that radio wave. You can do this because it behaves like a classical wave, lots of photons involved. So you can actually digitize the wave. And then, you have a digital copy. And then rather than having it go to the focus point, you just add the two up with a proper delay, which you need to calculate. And then you get the same output as a normal telescope would do. Now, if you do this reflection only in one point of the telescope, what you get is this interference pattern, because it's the two the waves are put on top of each other. And that's what you get if you have 2 points of your telescopes only reflecting. Yeah, everything else is masked. Or you only have two receivers, one here and one here on the one in the South Pole and one in this case here is in Spain. You put them on top of each other, you combine the waves, it becomes an interference pattern. Now, interference pattern is sensitive to the structure of the source. If you move the source a little bit, the interference pattern will change. If the source is a little bit extended, then light will take a little longer from one side to the other. So you have more or less interference. And so what you want is actually multiple directions and multiple points being covered. And so that's what we do here. We have multiple combination of telescopes, and they all produce interference pattern. And if you put all these interference patterns on top of each other, you recover the structure of the object. In this particular case, it's a teapot, not a black hole. But essentially, and if you would actually have all over the Earth, you would actually get a perfect reconstruction of an image simply as a mirror would work. Just for the specialists, every combination of telescopes measures a Fourier component of the image. And in fact, the longer the baseline, the higher the Fourier frequency that you measure. And so what you then need to do is, you measure these combinations and then they do a Fourier transform back and you get that image with some artifacts, but then these you need to clean out. But essentially that's the basic principle. And what you want to measure all separations and all orientations as much as possible. And that's why the rotation of the Earth is important, because it actually changes the perspective and it changes the relative orientation and the projected length of that baseline. So that's the basic principle. And so 2017, we did this first big experiment with 8 telescopes at 6 different locations. And so you have here a group in Hawaii, in Mexico, the South Pole, in Spain, in Chile, and Arizona. Again, there's an A missing. And it was a mixed international team that was present at these telescopes. From my group, we had actually people, I think almost all the telescopes except the South Pole, because it's a bit hard to get there. And you have to wait until next morning to come back home. And next morning is half a year later, right? For half a year it's dark and half a year it's bright. So people sit there, winter there, have 6 months of darkness at the South Pole, and only a few weeks of observations for the EHT. But they do other stuff as well. And so this was our crew here in Chile before the observations. Quite happy. We observed for almost 2 weeks, day and night. And we had perfect weather, which was also important. And so it was very tiring. So that's how they looked after the observations. Yeah, okay, good. I give you here, I was in Spain. So at the IRAM 30-meter telescope near the Pico Veleta, that's the telescope here in Google Earth. And just to give you a sense of it, you go up the mountain first with a little bus. That's in April. It's actually now a ski resort. When it was built, there was one ski lift. Now it's a big ski resort. You see the ski is already melting. In fact, the brown part is Sahara dust, by the way. So that's what amplifies the melting. They're still enough slow that the roads were not free, so we had to take that piston bully, as it's called in Germany. And with the crew of astronomers, not all of them from the EHT, they do other things as well with the telescope. You see some of the ski lifts in the background. There they are. And actually in the far distance, there is the Mediterranean Sea. And so, in fact, within a day, you can go observing, skiing, and swimming in the Mediterranean Sea if you plan it well. And again, you see here the pictures. Okay, this is the digital equipment at the telescope, which records the data on hard drives. This is a control room. Thomas Krichbaum on the right. This is a telescope, 30-meter diameter, really a big dish, operating up to 0.8 millimeters. Some clouds there, but actually this was clearing up. Yeah, this is the inner part of the telescope. This is where the receivers are. The light here is reflected by these mirrors, chopped off by this chopper here. Yeah, you can see me in front of this big propeller, which is the chopper, and that's the receiver where actually the light is digitized, and that's the atomic clock of it. And this was the crew. So that gives you a very quick sense of the pictures. Oh, the food was great. So this was, and she had birthday, so fantastic. Okay, and what you see here is actually typical observing night. You see the green triangles is when telescopes are recording, and then you see the targets moving across the Earth. It's actually the Earth rotating underneath the targets. These are M87 and then 3C273 and 3C279, which are famous bright quasar strong radio sources, which we take as calibrators, but also to check our imaging. And so as the Earth rotates, we get more and more telescopes can see the source, and we get more and more perspectives, more and more baselines, as we say, and the image will get better and better. And then you have to reduce the data. So this was the collaboration meeting in the Netherlands, in Nijmegen at my university in 2018. 110 people of the 300 people showed up. And then we showed that image at the press conference here in this case in Brussels, which was one of the two major press conferences. And we see here an animation now of that first that we showed at the press conference. We're zooming into Virgo from essentially the location of ALMA, and we zoom into the galaxy M87. You see this radio bubble there. And then we go to other images from other telescopes as that give higher and higher resolution. So these are radio VLBI images where you see the plasma jet shooting out, and then we go to higher frequencies, eventually the EHT. And then that's the image that we saw, that ring of light with this darkness in the very center. I can tell you it was a very moving moment when I saw that image. Even before that, we saw that image in the data. It was just amazing to see this because you've been thinking about this, dreaming about this for 20 years. You've made simulation. Suddenly you look at the real data and it shows you exactly what you were expecting. Some people call it just an orange donut. But honestly, if you know the story behind it, it's so much more. It's a story that turns it into something really fundamental, because in the very center, in that darkness, you're really looking into the abyss of a black hole, into the event horizon. You literally see that event horizon. Well, the shadow of it, obviously. I just want to quickly, say something which was very important for doing our science, something that was, hard fought, and something that we had to build up in terms of how we do our work, because everything we did at least 2 or 3 times in different teams, because there's only one experiment that can do this. We need the entire world, and the entire collaboration was working together on one image, so to speak. And there are multiple steps you have to do. You have to do the observation, you have to do the correlation, which brings together the data, you have to calibrate the data, you have to do the imaging, then you have to do some physics simulation to actually compare to, and then infer some parameters from comparing the data with the physics simulation. And everything we did, we had at least 2 groups, sometimes 3, sometimes 5 different groups doing the same thing. And then we would compare. Because that's what science is. Science needs checking. It's nice if someone does a nice image, that I will not believe you. I need someone else to check it. And we did this very intensely inside the calibration. Everything had to be checked and verified over and over again. And in fact, we are not only doing rings, right? We'd also do other sources. These two other Quasar 33279 doesn't look at all like a ring. Or Centaurus A, another radio galaxy, looks like this thing here. So we have different sources, different groups. So that's a way of really checking that you do the right thing. I get many people who say, totally convinced that they're right, and they have the right theory, the right data. But folks, need to check, and others need to confirm what you've done, and that is so important. And then we talk about doing science, and so that's what happened. Well, we showed that. You mentioned already the feedback from the world. It was really on the newspapers all around the world. 4.5 billion people saw that image, according to 2 different studies. The internet was going wild already at the time. In fact, the image was taken into the collection of the Museum of Modern Art and the Rijksmuseum in Amsterdam, sort of 2 major museums, because it had such a cultural value. And it even became part of Netflix movies, which here you go through a series of years. 2018, the fire in Notre Dame. 2019, the image of a black hole is being shown. So that's I got a WhatsApp a message from my kids saying, "Oh, Dad is part of a cheesy Netflix movie." So it really created a lot of buzz around the world. Of course, we've moved on since then. I realize I'm going a bit slow, but we've done more and more observations since then, many years since then. Of course, Corona was in the middle of all this, or very soon thereafter. Now we have more telescopes. We have here the blue ones in Arizona. There's a second telescope. In Greenland, there was another telescope. In France, there's another telescope that joined. You still see which continent is missing. We'll come to that at the end. We've now have published, and we have more data in-house, but the published ones are 3 images of M87. All show exactly the same ring structure. So the size of the ring is exactly the same. And that is the prediction, because that is dominated by the mass of the black hole. That shouldn't change as a function of time. Yeah, I told you the time scale for black holes of the size near the black hole is actually weeks. Yeah, if you observe a year later, it's many rotations, many dynamical time scales later, and we still have exactly the same size of that ring. What you see here, this hair, is not Beard Haircut Day. It is actually these lines indicate the polarization axis of the light. So light can actually swing in or oscillate in a certain plane. And that plane is related in a bit more complicated way to the magnetic fields where they're generated from. So what you're essentially seeing here is an indication of how the magnetic fields are oriented. You have to rotate by 90 degrees and do some GR corrections. Okay, fine. But essentially what it tells us, these lines, is the magnetic fields resemble what we expect from these simulations. I mean, that they stick out of this magnetic, out of the plane of the accretion disk. So that's how the magnetic fields are oriented, and that's exactly what we find in the simulations. So that seems to be confirming more or less our basic understanding how these plasma jets are being generated. Then 3 years later, we had this of Sagittarius A star. Similarly, we are zooming into the center of our Milky Way. You see the large-scale image. You see that few hundred light-year image of the center of the Milky Way with this beautiful Sagittarius A complex, that mini spiral in the very center that you see. And then this little dot that we've been chasing and trying to understand for decades now. And now with the Event Horizon Telescope, we are getting so close, so deep, that we would be seeing this, what actually is a ring. It looks like a triangle, but actually is a ring if you look at it with the dark region as well. And again, exactly the right size. Within the measurement area, exactly the right size. And so if you then put these compare these two things. This is a galaxy M87, and just to scale, this is Neptune's orbit. That ring is essentially sort of on the sky. So actually, in that ring has this, no, not on the sky. That ring sort of, if you were close to it, would be larger than Neptune's orbit. While that ring that we see in the center of the Milky Way, inside Mercury's orbit. So one is sort of the inner solar system, the other one is way beyond the outer solar system. Yeah, and the reason why they all look the same is just this projection effect I explained in the beginning. Yeah, because the left one is much further away than the right one. And I couldn't avoid putting in the prediction that we made 25 years ago. And, I always jokingly say we even got the color right. But obviously these are fake colors. So we used, we just defined it for artistic reasons, the intensity, an orange glowing color, which was supposed to represent, heat, glowing iron or something like that, which I thought at the time was representing black holes much better than rainbow colors or something like that. The black hole is not a happy place. It's it's a dangerous place. Okay, so stay away from them. And then, we later used the same colors to actually color the observations because it's radio frequencies. They are much redder than any red that you can see with your eye, right? And this is a polarization of M87 of galactic center. Again, the spiral-like polarization pattern on top of it, which shows that also there the magnetic field structure is very similar to the one in M87. So both black holes look remarkably similar. That's an amazing thing. And also their sizes are really spot on. What you see here is the mass on the bottom left, as the y-axis is the inferred shadow size. How big is that shadow? And then the red line is not a fit, it's a prediction of GR. If I have a black hole of that mass, that line tells me how big the shadow should be. And then you measure M87 and it's exactly on that line, within 10%. Then you can use, there's stellar mass black holes. I'm not going to go into details here. You can use gravitational waves to make an indirect shadow measurement. It's not direct measurement, it's indirect, but they also really confirm black hole general relativity at a scale of tens of solar mass of black holes. And so, these two measurements really, pin down the whole line, and then galactic center comes in. And of course, 2 points always fit on a line, right? The third one is the really interesting one, and it also fits the line. So it's really spot on again, even though it's, factor 2,000 or 1,500 away in terms of mass, it still is exactly within 10, 20%, or 15% or so on that line, within the error bars. So that's, I think that's amazing. We also compare these images with a range of simulations, actually millions of images that we simulated in the computer, and for all kinds of different parameters. Here below is the inclination, so you look from above, from the top of the black hole or from the side of the black hole. You have the strong magnetic fields or not so strong magnetic fields. You have highly spinning black holes here or non-spinning black holes. So all kinds of different parameters. They all show this shadow, and some of them fit better our data than others. And from that we can infer that likely we have we're in this regime of something that we are looking at face on. So not from the side, but more from the top for both black holes. And that magnetic field seems to be very dominant in this. For the spin, I hesitate to actually claim a number because we know the measurement of the spin, how fast the black hole rotates, is in fact difficult to infer. But anyway, so we have these simulations. Just to go on, we have made more observations. I'll just quickly wrap up here. We've now moved to higher frequencies. So far we have done 1.3 millimeter. Now we do 0.8 millimeter. So we're going from 230 gigahertz to about 345 gigahertz. We've made the first detections on calibrator sources, where we hope that we actually get a second frequency with images in the future. I'll tell you already, at these higher frequencies, the atmosphere becomes very difficult, and so it's going to be really tough to actually make images. But we'll do our best. This year, actually, we just completed a movie campaign on M87. Again, these are pictures from just a few weeks ago. Again, another campaign where we observed M87 every 2 times a week, more than for 2 months. What we see, we want to actually see how stuff rotates around the black hole, because we expect it to rotate within 2 weeks. So we should see some structural variation going on. So we want to go from still images to color images to actually movies and eventually color movies, right? So that's the goal. Well, that guy down here actually just got lost on the mountain. So that little bird here, it was released and is doing fine apparently. But it just was flying too high and was looking for shelter at the telescope. Now, of course, you notice already we are missing a telescope. In fact, many telescopes in Africa. It really limits our ability to make good images of black holes. Is that we so far do not have high frequency radio telescopes in Africa, millimeter waves, and so that means up to 345 gigahertz. There are telescopes in centimeter waves, and you know the square kilometer array, which may go up to 20 gigahertz, but we have to go a factor 10 higher. So that requires much better surfaces and other receivers. And so together with University of Namibia, University of Oxford, Amsterdam, now also University of South Africa, University of Tokyo University, and of course Radboud University as a lead, we're now building together a telescope in Namibia, which will first be placed near the Hess telescope at 1900 meters. On the farm Göltschau. This is where the famous Hess telescope is, and construction will start in the third quarter of 2027. So already next year we're getting there, and it's making me very nervous because many things still have to happen until you have a functional telescope. So that's going to be tough. So of course, eventually we want to go to the Gamsberg, which is a table mountain in Namibia, which is even higher. And what you see here on the top right is the additional baselines in red, are the additional connections that the single Namibia telescope would add. And so we see there are many triangles, many additional baselines that it will give us. And why is this important? If you have a model like this on the left, and you observe for the first east, there are many of the American telescopes are not yet observing. We have too little data. By adding, and so if you would make an image in the first few hours, you would see nothing. If you add one more dish in Namibia, you suddenly can recover that ring. It's just one telescope makes all the difference. Why is this important? We also want to look at the black hole in the Milky Way, and there it actually doesn't take 2 weeks to rotate. It takes 15 minutes to an hour to rotate. So you have to make an image every 15 minutes. And you cannot wait for more telescopes to come up. You have to make it right now. So we need a telescope in Africa to actually observe it and capture these. So we can capture something like for an hour or two, when Africa is right underneath galactic center. But adding the millimeter telescope will give us like 8 hours or 10 hours of good imaging. And so that makes a huge difference. And this is sort of a simulated blob going around the black hole. By just adding one telescope, we could be able to actually recover this. In fact, this is an old imaging processing one. We in the meantime have better image processing, movie recovering algorithms. So eventually, you want to move it to the Gamsberg mountain. And in fact, as part of this project, University of Namibia has bought that mountain. It belonged to the German Max Planck Society. They had bought it in the 70s legally, so that was all fine. I want to build a telescope there. but it was never built because Namibia at the time was part of South Africa. There was no scientific collaboration with an apartheid regime at the time, so that's why a telescope was never built. Now the mountain, Namibia is independent. The mountain now belongs to a Namibian institution, and so almost everything is fine with one little detail, and that so that was the mountain was bought, and actually University of South Africa joined, and they sort of jointly want to operate this telescope. So I think it's great to see some African collaboration now happening, and wanting to take ownership of the project. That little detail I mentioned is a road up the mountain, and you see the mountain. This is a current road, and I think, to my statistic, it belongs to one of the most dangerous roads in the world, essentially. It has like 40 degrees of inclination at the very end. So I saw a documentary about the most dangerous roads in the world, and they were all less steep than this one. So I think by that account, it is. So it does require a new road. We have plans for it, but it does cost extra money. And so, but you see this, this is a spectacular mountain, right? So, I mean, and perfectly suited for astronomy. So, yeah, I'll skip the space part here because I'm speaking already too long, and I'll stop here. And I hope that in a few years we regularly can make lots of observations from Africa and making fantastic movies. So AHT has seen a black hole shadow, I think twice, and M87 and Sagittarius has been confirmed now. I think multiple years, two different sources. So I think we can now say supermassive black holes are real. Right. So, I mean, it's really our, black holes are now, a supermassive black hole are a fact of science now. We know sort of they exist. Of course, there are always, discussions, could there be variants of black holes, or could we have changes of general relativity? That's what we're all testing. The shadow that we see really is the signature of the event horizon of the shadow. And then if you combine all of this, general relativity holds over 8 orders of magnitude, which is, I think, absolutely amazing to think that, it covers so many scales, and general relativity explains these black holes. We know a lot about the astrophysics. I didn't go into detail. I see my computer is a bit slowed down. We know the accretion has strong magnetic fields, powerful jets are produced, and there is potential evidence that we even extract some energy from the black hole spin, but that's something we still need to firm up. In the future, we now have 11 telescopes. We hope for Africa, we'll have Africa join potentially in 2028 or 29. Another telescope is built on the Canary Islands. I'm still hoping for a third telescope somewhere, and that would complete the array. And eventually we go to space. And then I think we can test astrophysics on general relativity on the percent level and really understand how black holes generate all the energy. And so I want to stop here. Thank you.
Wow. Thank you so much, Professor Felker. I'm sure, my brain is like, it's full. My brain is
sorry.
No, this is great. It's great. And I love all the background and all the information about the teams. And I think it's really, okay, so I'm more of an astronomy outreach person, and it's one of those questions that kids always ask about, black holes, because it seems like something fantastic that's not real. And it's wonderful to see, the real science showing, as you said, that these things are real and that you can see in quotes, see them, measure them. That's just brilliant to see. Well, Professor, you need to tell us how much longer you have. Is there time for a few questions? I know you said
we still have 15 minutes of question, or 10 minutes or so.
Okay.
I just, as a reminder, if I don't know if you want to look here for the more questions, again, are in this book here, the English version, Light in the Darkness. But there are also some other languages possible if you're interested more into this. So wonderful. I'll stop here the screen sharing, and then we can have a little Q&A session if you want.
Yes, yes. So there's a few questions coming in. I just wanted just to clarify first. So you're saying the African Millimeter Telescope, that one is not being built on the mountain. You said that one is near Hess, but then
No,
you hope
it's
ideally to go to the mountain first.
yes, yes. So we're waiting for some extra funds to actually make us go to the mountain.
Yeah. Okay. Okay, great.
But we wanted to start right away, right? So yeah.
Sarah, what about our telescope in Ghana?
Yes, I'm very much aware of it. You have a fantastic country. Unfortunately, it's a bit close to the equator. And I wonder, I suspect your mountains are not high enough.
Oh,
So that's why I always say that Namibia has an unfair advantage in that sense, because it's a very dry country and it has at least medium-high mountains. There is so the Ghana telescope goes to centimeter wave telescope, but we need to go to millimeter waves, and so there the humidity in the air actually is blocking the waves. So that's sort of the disadvantage that Ghana has. Yeah. But
so
for centimeter waves, we also be able to do centimeter waves at 8 gigahertz. I think the Ghana telescope for now only goes to 5 gigahertz, but if you could go
just a second. I think my okay, changed microphones here. We could do joint VLBI observation between Namibia, SKA, and Ghana if you go to higher frequencies, slightly higher frequencies. So that's
how can we achieve that?
Sorry?
How can we achieve that?
I don't know the technical details. I think you need at least 8. So we would need at least 8 gigahertz. Of course, you can still do VLBI without Namibia at 5 gigahertz. So in principle, that's possible. You don't need us to do this. But given that there are not yet so many telescopes in Africa, so maybe a relaunch of the African VLBI network at somewhat higher frequencies could be possible.
That would be cool. That would be cool. Jenny, I can see your hand is up.
Yes, indeed. Exactly on that topic. I was wondering, it seems at the moment that you rather have one streamline of Europe, Africa, and a bit in the US. What about China and Australia? I mean, Australia also has a lot of radio telescopes. So are they also joining at some point, or is this not planned?
Yeah, Australia has another problem, and that's it doesn't have that high mountains.
Let I come back.
So that's the problem.
Because I want to come back and do the flight.
There
going. You don't.
Someone else is talking, so we maybe should.
Well, I haven't finished.
Yeah.
Just a second.
I think Jacob, if you can mute yourself.
Yeah. Yep. Jacob, I'll do this. There are some discussions in Tibet. Chinese want to build something in Tibet, in the Himalayas, and India wants to do something also in the Himalayas. But I haven't heard what the current status is. The other one location, so South Africa would be an interesting location, obviously. And then they have 3,000-meter high mountain areas, which is good. And obviously near Kilimanjaro, right? So Ethiopia and other areas also has high mountains.
Okay, if I can
think
go.
it probably has to do with the way Africa is moving, right? Africa is probably moving, and that's where they have the highest mountains, and the mountain ranges in Namibia have already been sort of weathered away. So I think more the higher mountains are on the east of Africa.
Okay, thank you. If I can go, there are some questions in the chat. So Juspa has asked, can the location of the telescope, in other words, the observatory, play a role in achieving more detailed information about the black hole?
Yeah, no, that's exactly why we've chosen Namibia, because this was sort of a strategic location where, it was adding important, as we say, baselines, important additional data. In really, the image quality is directly linked to where the telescopes are. Yeah, and so there's a one-to-one. It's actually even mathematical relation to the telescope location and the quality of those images that you can calculate. And indeed, because the center of the Milky Way is in the southern hemisphere, right? It's south of the equator. You want to have telescopes south of the equator, and Namibia is almost exactly underneath the center of the Milky Way. So it's I think 4 degrees away from zenith, or 6 degrees, and so that's perfect. And again, Ghana is more northern. That's good for M87, but again, the frequency is not high enough.
Okay, thank you. And then Martina has 2 great questions. One is, well, maybe the first one you've talked about a bit, maybe just briefly. What were the main challenges your team faced when imaging a black hole? And then the second one, which I think is a great one, what criteria are used to decide which black hole to image next?
Well, let's start the second one, and that's pretty clear, because it has to be big enough, right? It has to be big enough and bright enough. And the fact that both of these sources were not only the same size, but also the same brightness, is very unusual, but just good enough. And there are currently no other black holes that are actually big enough that we can see from the ground. And that's just given by the size of the Earth. In fact, the Earth is just barely big enough to make images of those 2 black holes. And so in that sense, there is no real choice, right? So it's already, nature has told us what we need to do. Of course, we can go to space, and then the separation between telescopes can be even larger, and we can go to higher frequencies. And so there we can get a factor 10 better, and we can see more black holes. And then we are sort of investigating some of them to see, how bright are they, how compact is the emission, and so we do preparatory observations. And there are, of course, many other black holes where we do not see the black hole itself, but the plasma jets. And they're also being studied. And there are many arguments for, well, this is better than this one. So many groups looking at different black holes. And the main challenges were many. You had to go to much higher frequencies. So we had atomic clocks that had to be shown to be stable enough. We were developing really very new imaging algorithms as well. To be honest, but the biggest challenge was just getting the entire group work together and organize itself. It's 300 people who from by now more than 60 institutes really, 60. There are 13, 14 stakeholder institutions which will take most of the funding and input, but many different groups who used to work in competition, and now they have to work together to achieve one common goal. Yeah. And so getting from that mode of competing against each other to, we are one group and we have to achieve this, and we have to plan this, we have to organize this, we have to organize ourselves, was not an easy thing. And we're already going quickly into all this activity while weren't even finished with all the organization, and we didn't even know each other. So it took a while, I think, to get into sort of calmer waters, but it was a lot of enthusiasm, a lot of energy at the beginning, and now it's sort of much more stable work. Yeah. And of course, other factors like the weather. You have to have good weather all over the world, or at least where the telescopes are. And again, this was one of the things in 2017. For almost 2 weeks, we had perfect weather everywhere. So, and some other factors which were pure luck. I mean, it's science is always planning and preparing, but there's always an element of luck.
Great, thank you. So I'm just so people know, I'm kind of picking out, because I know Professor Falco needs to go at some point, so I'm kind of picking out, not necessarily going through every single question in turn. But so Ron Ryan asked, is there some kind of reconstruction bias to avoid or use when comparing the imaging algorithms of M87 and Sagittarius A star black hole shadows?
Yeah. That's, of course, a very important question that we asked ourselves. And I was very nervous about that. I mean, I try to calm down everybody because, if you find something that you wanted to find, that's the most dangerous thing in science, right? So you have to be very critical of yourself when you find the desired result. And so that's why we split up in these multiple teams independently, and they were not able to share the information with each other. And then after the fact, we unblinded sort of their results and compared them. That was one step. And then the next step was that every image algorithm had to show that it can reconstruct very different types of images. I skipped that view graph. I'm apologies. So, they are not tuned to just recover rings, but there could be double sources. At some point, there was even a snowman or other structures that they had to recover. So yes, the algorithms are not tuned towards image rings. You can tune them to actually give better rings. And then you would get better images, but then you would have that bias. And we try to avoid that. In the future, this may actually change while we add up more and more data. Sort of the structure will stay the same. We can use that information to actually improve the images. And then there is an intended bias. Will there be in there? But then we've already established without bias that the structure is a ring.
Okay, thank you. Okay, a question from Samuel. I mean, okay, so he's asking, will you get the same images if you observe in infrared, visible light, or even UV? I guess he's asking, why are we looking at radio? Yeah.
It turns out that the emission actually peaks, so it's strongest here in the millimeter range. There is near-infrared emission as well from related processes. And the expectation is that if you look at near-infrared, I would expect to get a very similar image, maybe even sharper. But for that, we would need to build interferometers with kilometers baselines in the near-infrared, and that hasn't been done. It is conceivable that this will happen within some people's lifetime that are on this call. Not sure on my lifetime, but that could happen. So yeah, ultraviolet, I suspect we will not see. And then you could build an X-ray interferometer in space, but I think that is going to be decades and decades away again. Yeah, but in principle, yes.
Great, thank you. Do you have time for maybe one more question?
Yeah, let's do two more questions.
Okay, two more questions. Thank you.
I talked too long. It was my own fault, so I apologize.
We're all enjoying. Okay, so Anno says, what are the major promising results and its correspondence and new features identified so far?
Yeah, no, I think we want to look at the dynamics of black holes. So really try to make images. We could already do this with the first, with the data we have. So we'll work on this. But then we need statistics. We need many more. And from that, we hope that we really get a better handle on the spin eventually of the black hole, but also on the astrophysics. There's still some little bit of uncertainty about the magnetic field configuration. And we see actually things changing now, which confuses us a little bit in the magnetic field. So we'll try to understand that. And so getting the spin nailed down, getting the plasma ejection mechanism nailed down. So really the real hard work is starting now. I mean, the excitement, we showed it works. We have the ring, but now we get to this real science and get the parameters nailed down, the errors nailed down and so forth. And that just takes patience and time. Yeah. And eventually, I mean, in space, I'm not sure we can show this from the ground, but in space we'll try to see spin energy extraction from a black hole, which is also a very fundamental process.
Great, thank you. And then I think we have the last one here from Kwame. What role did laser interferometry and gravitational waves play in the identification and detection of this specific black hole?
Actually, in this case, none. Because they don't emit gravitational waves. Gravitational waves only you get when you have like two sources orbiting around each other. Here we have only one big source, and the metric doesn't change and does not produce gravitational waves at all. I mean, very tiny ones from stars or something small things falling in, but that's undetectable. And so that's actually good in a way, because gravitational waves also need to take the dynamics of general relativity into account, while we measure actually just the static situation. We just measure the metric of space-time. In gravitational wave measurements, the measurement of space-time and the equation of general relativity are intermixed. So to some degree, we have a cleaner signal in some aspect. But we are also complementary. But we're not looking at the same sources. They look at much lighter sources, and we look at much more heavy sources. This will change in the future with Space Interferometer LISA, which will actually see how two supermassive black holes will merge. But it will not be those two. The really golden bullet, but I don't think it will happen if you'd have a space interferometer and we would actually have two supermassive black holes merge, emit gravitational waves, and we would be able to see both of them. But you'd have to be so extremely lucky that they both, large enough and bright enough, and both spacecrafts are operating, that this are probably unlikely. But that would be really cool. Technically, in principle, possible.
Thank you. We will be looking forward to that. So
Yes.
I think for time, I think we'd all just like to say a huge thank you to Professor Falco for that really fascinating presentation. I mean, into all the details, and yet, clear enough that we can all understand it. I love this. I mean, what you've done is amazing, but I love that we're still looking for more. And again, this is something I always say to students, to young people, it's great that we don't know this, and this, because this is for you to look into as you're growing and as you're studying. There's always more. There's always more out there in astronomy. So thank you very much, Professor. Thank you everybody for joining and for all your questions. It's been a wonderful session, and yes, hopefully we will share the recording so everybody can enjoy it, and look out for our next talks.
Okay. Have a great day. Bye-bye.
Same to you.
Thank you.
Bye-bye. Thanks a lot.
Thank you so much.
Thank you, Jenny.